Archimedes and the crown conundrum. Archimedes of Syracuse was a Greek mathematician famous for coming up with several mathematical and physical principles, including finding the area of a circle and the volume of a sphere. This story starts with King Hiero II of Syracuse. He had a crown commissioned to be made for a temple and had supplied the gold to make it. However, once the crown was returned to him, he began to suspect that the crown was not made of pure gold, but silver had been added in. He hired Archimedes, who was well known by then, to find out if he had been cheated or not. This was a mathematical conundrum. Knowing that gold has a very specific density, a crown that was not pure gold would be less dense than one that was pure. The problem was that to calculate density, the volume is needed, and a crown is a very unusual shape indeed. Archimedes had been told he was not allowed to damage the crown in any way, so melting it down to make it a regular shape was not an option. One night, when he was getting ready for a bath, he accidentally filled the tub way too much, so the water was sitting at the rim. Naturally, when he got in, all the water sloshed over to the side of the tub and onto the floor. This was when Archimedes had the idea. The volume of water displaced by the object will be equal to the volume of the object. Eureka, he shouted, running down the street. I have found it! Eureka! Eureka! He was then able to conduct a test by submerging the crown in water to get its density and to find out that silver had indeed been mixed in.
Hello, my name is Jose, and I'm a summer camp counselor at the Lowell Observatory Camps for Kids. And today, we're going to do one of our science challenges. For this science challenge, we're going to learn about the Archimedes principle and measuring the volume and density of irregular shaped objects. So volume is the amount of space that something takes up. The density is how much stuff is contained within this particular space. Right? For example, I do have a list of densities of different objects in here. So helium, you know what helium is? It's the stuff that goes in balloons. It makes it rise. Helium is not very dense at all. It is only 0.00009 grams per cubic centimeter. So this thing is really, really tiny. So we're going to talk about how much stuff is within this tiny little box. Air, the stuff that we breathe, right, has 0.001293 grams per cubic centimeter. Right? We're going to get even heavier now. We talk about water. So water ice is less dense than liquid water. That is about 0.92 grams per cubic centimeter, whereas water at 4 degrees Celsius, just a little bit above freezing, is 1 gram per cubic centimeter. Now, we just watched a video about Archimedes weighing a crown and measuring whether it was pure gold or not. So, silver has 10.5 grams, while gold has 19.3 grams per cubic centimeter. So gold is actually one of the densest metals that we come across. So, we're going to go ahead and do the experiment now. For this experiment, we're going to need just any box that you have. You're going to need a ball, something that you're okay with getting wet, something you're okay with dunking in water. I have this rock. We're going to need some string, a measuring cup, a pitcher or a bowl. I have conveniently supplied a unit conversion chart as well as some formulas at the bottom of the lesson plan, which goes along with this video. I also have a notebook. I'm going to want to take notes. A calculator, always helpful. A food scale, a bathroom scale, your bathtub. Baking tray, I just got it out of my kitchen. So let's go ahead and start. We're going to measure the volume of our regular shaped objects first. So we call these regular shaped objects because we can measure the dimensions of them and just calculate the density. We're going to start with the box. It's going to be the easiest. To measure the volume, we're going to measure the lengths of all the sides, right? The length, the width, and the height. So I'm going to do that. I've got a meter stick that I have sort of attached to my table, and I'm going to use that. I'm going to measure in centimeters to do this. So first, we're going to start over here, maybe 9.3 centimeters. So I'm going to write in my notes, 9.5 centimeters. We're going to go to the next side, do it again. 6.5 centimeters for the width. Last but not least, we're going to measure the height. All right, we're going to measure this length right here. 8 centimeters in length. To calculate the volume of a cube or a rectangular prism, you will need to multiply all the lengths of the different sides together. So we're going to take 9.5 centimeters times 6.5 centimeters times 8 centimeters. And we're going to just go ahead and punch that in the calculator. 494 cubic centimeters. So that means that the volume of this box is 494 of these little guys. Now we're going to measure the volume of the sphere. This one's going to be a lot harder because, as you can see, we don't have like a length or a height. It's kind of round. It's going to be a lot harder. What we need to calculate the volume is the radius. The radius is the distance from the edge of the sphere all the way to the very middle. We're going to have to calculate the radius. So we're going to measure the circumference instead, right? We're going to measure it at its widest point all the way around. We're going to try. That is the length of, or the circumference of my sphere. 44.5 centimeters. To calculate the volume of a sphere, we're going to have to do a little bit more work. So we have measured the circumference, right, the distance around the widest part of the sphere, and we're going to first have to find the length of the radius, which, if you remember, is the distance from the edge of the sphere all the way to the very center. And to find the radius of a circle, we're going to have to remember that the radius is equal to the circumference divided by 2 times pi. So for those of you who haven't seen pi before, we're going to use, this is a Greek letter, right? The Greek letter pi is approximately equal to 3.14. That's what we're going to use. As many of us already know, pi is an infinitely long number where it just keeps going and going and going, and it has no end. So we're just going to plug in all of the numbers that we have. So the radius is going to be equal to 44.5 centimeters divided by 2 times 3.14. So we'll enter that into the calculator. 7.02308.239. All right, so now we have the radius, and now we can find the volume of a sphere. To find the volume of a sphere, we're going to use the formula, the volume, V, is equal to 4/3, right, the fraction, times pi times r cubed. If you haven't done exponents yet, we can rewrite this as 4/3 times pi times r times r times r. Right, so r cubed is just r multiplied by itself 3 times. Right, so we can go ahead and we'll plug in those numbers. So we'll have 4/3 times pi times 7.0829 cubed, right? And that will give me 1,488.08945 cubic centimeters. just in this sphere that I can fit in my hands. There's almost 1,500 of these just inside this little sphere. The next thing that we're going to go ahead and do is we have to measure the weight. Remember that density is how much stuff is contained in one small area. And to figure out how much stuff that is, we need to find the weight. The weight will actually help us learn what the mass is. Mass is the amount of stuff that something has. Right? So we'll go ahead and measure the weight of our cube first. And I'm going to go ahead and weigh it on my scale. And it looks like I'm getting 25 grams. Let's go ahead and measure the sphere. 34.5 grams. All right, now we're going to go ahead and calculate the density of the cardboard box. So what we're actually finding is the average density of this box. We know that it's made of cardboard and it's filled with air. It's not the same, it's not solid, it's not the same all the way through. So we're actually going to find an average of the cardboard and the air while we're doing this. I predict that the density will be very low. It will be denser than air itself, right? But it will probably be very close. So let's go ahead and do that. So again, density is going to be measured in grams per cubic centimeter. So how many grams is in this one little centimeter, right? And so it's pretty intuitive after this. We're just going to go ahead and take the mass, which is 25 grams, divided by the volume, which is 494 cubic centimeters. So I'm going to use, you don't have to do this, you can call it D if you would like. I'm going to use the Greek letter rho, right? I'm going to say that is what the density is. Rho is equal to 25 grams divided by 494 cubic centimeters. I got 0.0506 grams per cubic centimeter. The density of air, as it turns out, is still much smaller at 0.001293 grams per cubic centimeter. All right, now we're going to calculate the density of the sphere. Now, unfortunately, this was my only ball that I had in my house, and I think this is kind of a bad example because if you can see, it's really heavy on this green side, and it's really light on this side. That's because this is filled with air, and this is not. And it allows it so that this ball can't roll, so my cats can play with it. Right? So since this is not uniformly distributed, again, we're finding an average density of the entire sphere, and it's not going to be the density at any one part of it. So we're going to go ahead and do that. We have the mass right here. So just a reminder, the density is rho is going to be equal to the mass, 34.5 grams, divided by the volume, 1,488.09 centimeters cubed. So we're going to punch that in the calculator, and we have an average density of 0.02318 grams per cubic centimeter. All right, now that we have calculated the volumes of these regular shaped objects, we're going to go ahead and do something a little bit more difficult. We're going to get this rock. We're going to do the same thing, but we're going to have to do a different method. Right? So what Archimedes did is he placed objects in water, and he saw that the water's volume displaced. Right? He found out that the volume of the object was going to be the same volume of the water that gets moved when you put something in water. This is part of the Archimedes principle, right? It's named after him. It's really famous. So we're going to go ahead and we're going to measure the density of this rock. So I'm going to measure the weight first. All right. I'm going to put the rock on my food scale. Nice. I got 971 grams. And then we're going to do the fun part, the wet part. We're going to go ahead and we're going to dunk this in some water. All right, so we're going to go ahead and we're going to measure the volume of this rock. So I've already cleared off my area, just, to avoid getting anything wet in case I mess up. Right. I've cleared off the area. I've got my pitcher inside this tray here, and I have filled the pitcher as far as I can fill it without water coming out. So it's not all the way to the top, but if I add any more water, it will spill over. And then I've got my rock. So one of the things that I've done, if you use a bowl at home, you probably don't have to do this. I've actually attached a string to it. I've attached a string so that way I can gently lower the rock into the pitcher without causing a splash, right? And so that's how I'm going to get it in there. Now, as I lower the rock into the pitcher, the water will rise, it will come out, and it will go into the tray here. And this is the water that I'm going to measure to find the volume. So let's go ahead and do that. I definitely have had an accident over here, but that's okay. But you can see the water's at the exact same level still. The water spilled out the side, and it's now in this tray. We're going to move the pitcher very carefully without spilling any more water. And now we have this water in this tray. We're going to put it in the measuring cup. There we go. All right, there we go. We have the volume of water that was displaced by the rock, minus a little bit that got on the table. So we can use this to measure the volume of the rock. So this is in milliliters, just about 300, we're going to say. So we've been using cubic centimeters. So we're going to have to change 300 milliliters to cubic centimeters. And so we're going to have to calculate that right now.
Let's calculate the density of the rock. So this rock is basalt, and basalt usually varies from 2.8 to 3 grams per cubic centimeter. So that's what I predict the density of this rock will be. We're going to have to convert volume from milliliters to cubic centimeters first. So to do that, all we need to know is that 1 milliliter is equal to 1 cubic centimeter. We don't even have to do any calculations. We now know that the volume is 300 cubic centimeters. That was pretty easy. Now we can go on to the density part. Just a reminder that density is mass divided by volume. So we're going to take the mass, 971 grams, and divide that by 300 cubic centimeters. And we'll punch that into the calculator right now. And we have 3.237 grams per cubic centimeter, which was very close to my prediction of 3 or 2.8 to 3 grams per cubic centimeter.
Hey again, it's me. In case you noticed, we're in a completely different room now. So we're actually in my bathroom, and what we're going to do now is we're going to find out what my density is. So we're going to take the same concept that we did with the rock when we poured it in the water, and we're going to do that with myself. Since this does take up a lot of water, I suggest doing this at bath time, at your regularly scheduled bath time, so that way you don't use up more water than you need to. So I've already filled up the water in the bathtub. It's ready for me to go, right? A few things that I've also gotten, got some tape. I have a measuring cup. Again, the same measuring cup. And because I'm going to be measuring, I also have this bin. It's just a storage bin that I've had, that I had some stuff in, right? So the concept, this is what I'm going to do. I'm going to get myself in. If you notice, the water isn't all the way at the top. And that's because I don't want to have to mop up all the water that lands on the floor. And I don't think that you want to have to do that either, or your parent doesn't want to do that. So instead, I filled it up to my normal bath amount. It was a little bit more than I probably normally do, right? And what I'm going to do is I'm going to get in, and the water's going to rise. So I'm going to actually put a little piece of tape on the water line right there to mark where the water is at now, right? It is already pretty humid in here, so that means that this isn't sticking very well. So you do have to think about that as well. So it's at the water level, and when I get in, we're going to see the water level rise. And then my goal after that is I'm going to use the measuring cup to take out the water, put it somewhere else, put it in this bin, until the water level's back down to where it's supposed to be. So this is going to take some time. I'm going to have to count. Now my measuring cup, as you can see, goes up to 500 milliliters. That's a half a liter. So this is gonna take me a while. What I'm gonna do is I'm going to count how many half liters I put in here, and then I'll figure out how many cubic centimeters that is afterwards. I've also got a bathroom scale in here, so I'm going to weigh myself, and then we're going to figure out what my density is. Have got in, and I had to redo the tape because immediately upon getting in, the tape flew off. So I had to get out, and I had to retape it, right? So now that I'm all the way in, you can see that the tape is now completely submerged in water. So that's how much the water actually rose, right? Because I put the bottom of the tape at the top of the water. Now, there is a problem with the fact that I'm actually too big for my bathtub, so I won't be able to submerge myself completely and be able to have all of me in. So we're going to go ahead and we're going to begin. So again, I'm going to measure this in half liters. It goes up to 500 milliliters. This is half liters. I'm going to count how many half liters it's going to take to get the water level back down to the bottom of the tape. I'm going to put all of that in here, just so I have some place to put it. All right. Let's go ahead and begin. So I'm measuring 1/2 liter, pouring it in my bin. All right, 2. Yeah, so there you have it. I'm right at about 69 half liters, so 34.5 liters, that's my volume. And so I can take that, multiply it by 1,000, 34,500 cubic centimeters. That's my volume. I'm not going to calculate my density, but I will make a prediction as to what it is, and you tell me if I'm right or not when you calculate your density. I predict that since water has about 1 gram per cubic centimeter, it'll vary depending on its temperature, but I predict that since I am able to float, that my density will be less than 1. So you figure out what yours is, and you tell me if it's less than 1 or not. That being said, that does conclude this science challenge. this concludes the experiment. So what you're going to go ahead and do is you can do all the stuff that I did. You can take the volumes and densities of various things around your house, right? And you can take your own density using the same method that I did. That being said, feel free to like this video and subscribe to Lowell Observatory. Follow us on Twitter and Facebook. And then once you figure out what your density is, go ahead and give us the answers. Go ahead and tell us. You can send it to us directly. The link should be provided somewhere in the description, as well as you can just put it right on the Lowell Observatory Camps for Kids Facebook page or the Lowell Observatory Facebook page. Yeah, I'll see you next time in the Science Challenge.